Okay, so in this video, it's the start of our new topic, which is called Other Graphs. And throughout this topic, we're going to introduce a number of new graph shapes that we haven't met before. And that's going to require us to it's going to actually give us a vehicle with which to introduce or to further extend our understanding of a couple of things. One of which is our understanding of functions. We have used that word somewhat loosely up until now, so a clear understanding of what it is for something to be a function, what has to happen for something to be a function, and also a review of function notation, which we did look at in semester 1, but there are some new students to the class at this point, so we'll just again recap that, and also some recent assessments and videos have suggested that's an area that's a bit sometimes not very well understood. So we'll have a look at that here. We're also going to be throughout this topic starting to, or continuing I guess, to talk about transformations of graphs. And we want to be able to formalise the language, but also extend our understanding of those transformations from where we've introduced them through the parabola. We've talked about them again through the cubics and quartics in the previous topic. We now want to extend them to a whole lot of other graph shapes. And doing that successfully requires, or it is helped by, some sound understanding of function notation as well. So the topic is called Other Graphs. It is about graph sketching. Graph sketching is an important part of the Maths Methods course that you're aiming towards. But it's not just about learning about graphs. It's about building up our understanding of transformations and how they affect different functions and what that looks like in the equations of those functions, and also brushing up on our understanding of function notation and what it is for something to be a function. So this video we want to just focus on that latter point. So we're going to start by talking about this idea of relations versus functions. So every relationship between two variables, and commonly we use x and y to represent those two variables, but they might be, different letters. We've looked at examples where we've looked at time and height, and the variables have been t and h. So it doesn't matter what you call the variables, okay? The variable that goes on the horizontal axis, x, t, whatever it might be, versus the variable that goes on the vertical axis, y, h, whatever it might be, okay? So every relationship between two variables, regardless of what you call them, can be shown as a line, curve, set of points on the Cartesian plane. So you're going to be able to represent that relationship through some set of markings on a Cartesian plane. Okay, as I said, whether it's a straight line, whether it's a curve, whether it's just a couple of points, individual points, we should be able to represent that relationship. And anything that can be drawn on the Cartesian plane, so any relationship between two variables is called a relation. Okay. Only some relations are functions, okay, and specifically a relation in which each x value produces only one unique y value is called a function. The use of unique there, just be careful about how you interpret that. So each x value produces only one y value. So let's consider the following two relations. Y equals x squared, which we're quite familiar with, and a slightly different relation, y squared equals x, which we're not very familiar with. Okay, so let's work on the left-hand side here. So we want to complete the table of values for this function. Okay, so when x is equal to -3, y is equal to -3 squared. Careful how you write that. If you're going to write it, it must have brackets. If you write -3 squared, it's not the same thing. So -3 squared would be +9. Okay, so from this one x value, we've produced only one y value. Okay, if x equals -3, y has to equal 9. It can't equal anything else. Okay, if x is equal to -2, y is going to be equal to 4. If x is equal to -1, y will be equal to 1. If x is equal to 0, y is also equal to 0. If x is equal to 1, y is equal to 1. X equals 2, y is 4, and x equals 3, y is 9. Now, it doesn't matter that there are 2 points on the in the relation that have the same y value. That's not the issue. It is that for any x value that I pick, there's only one y value that goes with that. Okay, so each x value, just one y value. This is an example of a relation. Now obviously I've only looked at 7 different points. We would need to know that for every single x value we only get one y value, but if we have some understanding about what's happening with this function, and similarly if we think about the graph, we can verify that. So if we plot out this graph, we're very familiar with the graph of y equals x squared by now. However, if I've got a scale and a clear grid, I need to make sure that what I'm drawing is accurate. Okay, it should actually, if it's meant to go through the point 0.24, it should actually go through the point 0.24 because there is a clearly marked point called 0.24 on this gridded axis. Alright, so that is y equals x squared. So what we're seeing with that shape, hopefully, is we could pick any x value. So we know when x equals 3, we get just one y value where y is equal to 9. Okay, but we could think that through for any other point. You know, some point in the middle here is going to be equal to just one unique y value. It'll be that y value that that x value gives with this particular function. And you know, right out over here further on, obviously it'll be higher up, it'll be a bigger y value, but there'll still just be one y value. Similarly, right down here at a big negative value, there'll be just one y value that goes with that big negative value. It will be a big positive y value. Okay, so this is an example of a function. For any x value I choose, there's just one y value. Okay. Let's have a look at y squared equals x. So if you think about y squared equals x, that is y equals positive or negative square root of x. When we take the square root, we get plus minus. So for example, if x is negative 2, this is y squared equals negative 2, which means that y is plus or minus square root of negative 2. Now, we know that we can't square root a negative, okay? So this is actually not defined. And the same would be the issue with negative 1. Alright, if we think about x is equal to 0, so y squared equals 0 would mean that y is equal to plus or minus 0. Plus or minus the square root of 0, whether that's plus or minus 0, positive 0 and negative 0 are the same thing, so it's just 0. Okay, so far we're okay. So it doesn't, this x value doesn't equal any y value, that's okay. It just can't be more than one y value, okay? So this x value corresponds to just this one y value, so that's all good. Let's have a think about when x is 1, so y squared equals 1, which means that y is going to be equal to positive or negative square root of 1, and so that's positive or negative 1. So there's two y values there, plus or minus 1, okay? So we might write that as separately so we can see clearly that there's two values. If x is positive 1, y could be positive or negative 1. So in terms of with this being a function, this is a problem, okay? It's not a function here because for that particular x value, y could equal two different y value. Y could be two different values, okay? And the same will happen with the other positive x values. So if y squared is equal to 2, that means that y is plus or minus root 2. Positive root 2 or negative root 2. If x is equal to 3, y is going to be positive root 3 or negative root 3. If x is equal to 4, y will be positive root 4, which is 2, or negative root 4, which is negative 2. So two possible y values. Okay, so we've got problems here. Okay. So not a function. If we have a look at the graph of what that looks like when something isn't a function. So let's plot out some points. It's going to be easier to plot out just the whole number of points. So we go through 0, 0, that's fine. We go through both 1, 1 and 1, negative 1. We go through 2, root 2. Root 2 is about 1.4, sorry. We go through 3, root 3. Root 3 is about 0.6, so a bit higher than that. And 4, plus or minus 2. So we've essentially got a shape that does this. It's a sideways parabola. It's connected to the parabola. You can see the rules are similar. We just swapped where the squared is happening. So this is not a function because I could pick an x value and that x value corresponds to two different y values. So the fact that it corresponds to two different y values means that it is not a function. Okay. So one way that we can test graphically for whether something is a function is by using what we call the vertical line test. And essentially that is, if I draw a vertical line over here, just for a minute, and then see if I can get my program to do this. So if I take this vertical line and imagine swiping it across my graph, if at any point that line would hit more than one point on the graph, that's indicating that it's not a function. And that's because if we hit more than one point on the graph, that means there are 2 points here with the same x coordinate. Okay, so they've got the same x value. Let's say that's, I don't know, 6.2. and there's two different y values, whatever that y value is. It'll be plus the square root of 6.2 and minus the square root of 6.2 in this particular case, okay? And so that x value corresponds to two y values, and that means that by definition it's not a function. So this idea of the vertical line test is, you've got to imagine being able to sweep a vertical line across the graph like a barcode scanner, and if at any point that vertical line hits the graph more than once, that graph is not a function. Okay, or that graph doesn't represent a function. Doesn't matter if back over here it doesn't hit the graph at all. Here we only hit the graph once, so it's all good there, but the minute we go past here, we're hitting the graph twice, which means these are x values where there are 2 points, x values with two different y values. So by definition not a function. If we take our vertical line and swipe it over something that is a function, and again we're imagining this graph goes on forever, so it's a really big y value here. We're seeing that in this case, my red vertical line only ever intersects with the graph once, okay? And so therefore, by definition, that is a function. Right, so the vertical line test is key for being able to determine whether or not something, graphically, whether or not something is a function. But it comes back to this idea that it's all about every x value has to match with just the one y value, okay? It's not true in reverse, so you'll see here that, this y value of 6, there are two x values that go with that. That's okay, that's not an issue. That doesn't stop it being a function, but each x value has to match with just one y value, so we have to pass the vertical line test. Okay, so example 1, in fact both these say the same thing, so let's add a word in here that is not a function, okay? So I want you to just pause and have a go at this. So it doesn't matter, you're all going to draw different things. On the axis below, draw an example of a relation that is a function. So a relation is anything you can draw on the Cartesian plane. Dot, line, curve, smiley face, house, whatever. Draw something that is a relation and is also a function. So must meet this vertical line test condition. In part B, draw an example of a relation that is not a function. So it doesn't pass the vertical line test. Okay, so something that is a function, it can be squiggly and bendy and it can do whatever you want as long as it doesn't bend back on itself like that. Okay, so as long as, if I were to take my vertical line and swipe it across this graph, I would only ever be intersecting with the black curve at one point. Okay, so yes, we're all good there. Whereas something that is not a function is going to be sort of bending back on itself this way. Okay, so we would have issues. We would have issues with something that bends. That bends this way, because when I swipe my vertical line over that, we're going to be crossing the graph at. We're going to be Gotta let go of the line. We're going to be crossing the graph at more than 1 point. Okay, so not a function because of that. So as I said, you can draw whatever you want as long as one meets the vertical line test, hence it is an example of a function, and one doesn't meet the vertical line test, hence is an example of a relation that is not a function. Okay, so we've met function notation before now. We reviewed it a little bit at the start of the polynomials topic, and I'm going to just review it again here, but we should be getting really familiar with this now. It's really important. It's really important for you to be able to use the notation accurately. It actually also it's really important in helping you be able to use your CAS correctly, because your CAS makes good use of function notation. It makes you more efficient with your CAS if you can use function notation. It also makes you more efficient on paper. I've just finished marking some tasks for my Year 11 students where they sort of were writing out lots of things which would very easily have been expressed by using f of x or h of t or whatever the equation was, rather than writing out the equation every time. Okay, so being able to make use of this is really super important. So as I said, that we've met it before. So all functions can be written, so only if something is a function can it be written using function notation. So if it was a relation, so this y squared equals x up here, we wouldn't be able to write that using function notation, okay? Because the input doesn't produce a unique piece of output. So the whole idea is that when you have a function, the output is dependent only on the input, okay, uniquely on the input. So if I apply the function to whatever the input is, so the x value, I'm going to produce a piece of output, so a y value, okay? So for example, on the previous page, we established that y equals x squared is a function, so we can write it using function notation. F of x equals x squared. For this function, we know that f of 0 is 0. That's because when we replace x in the equation in the function with 0, we get 0 squared. When the input value is 0, the output value is 0 squared, which is 0. Okay. The second one, when f is f of 2, means we're making the input 2. So we're substituting 2 in place of x. It becomes the input. So if the input is 2, for this particular function f, the output is 2 squared, which is 4. Okay. Here we see that f of negative 1 equals f of 1, which equals 1. So that's essentially two separate statements. That is that f of negative 1 is equal to 1, and f of 1 is also equal to 1. And so therefore those two things must also be equal to each other. And that's true for this particular function. It's not true for all functions, it's true for this function. When you substitute negative 1 into this function, when you make the input negative 1, the output becomes negative 1 squared, which is positive 1. When you substitute positive 1 into the function, the output becomes positive 1 squared, which is also positive 1. So both of these things are equal to positive 1, and therefore that means that f of negative 1 is equal to f of 1, both of which are equal to 1. Same is true of f of negative 3 and f of positive 3 for this particular function, not all functions. This particular function that we've chosen to call f. Okay? So f of negative 3 is equal to 9, and f of positive 3 is equal to 9. And therefore, those two things tell us that f of negative 3 is equal to f of positive 3, which are both equal to 9. Okay? And we also know things like, f of x is equal to 25 when x equals positive or negative 5. So we know that when we make this function equal to 25, so if f of x equals x squared, f of x being equal to 25 means that x squared is equal to 25. And so we can solve that and get x is plus or minus root 25, which is plus or minus 5. And so what this tells us, another way we could write this same information, is that f of 5 is equal to 25 when x equals 5, the function equals 25, and f of negative 5 is equal to 25 when x equals negative 5, the function also equals 25. Okay? And again, we could write it like the previous sentence. We could say that f of 5 is equal to f of negative 5, which is equal to 25. Okay? So f is just the name of the function. This function is called f, and it means that we take the input and we square it. Okay? We could have another function called h, for example. So h of x, when we apply the function h to the input x, we take that x value, we add 1 to it, we cube it, and then we add 8. And so for this particular function, we know that h of 0, so when we make the input 0, requires us to add 1 to 0, cube it, and then add 8 to it, which gives us 1 plus 8, which is indeed 9. Okay. H of negative 2 means we make the input negative 2. So we apply the rule h to the number negative 2, which means that we take negative 2, we add 1 to it, we cube it, and we add 8 to it. Negative 2 plus 1 is negative 1. Negative 1 cubed is negative 1, plus 8 is 7. So h of negative 2 equals 7. We also know that h of x is equal to 0. Okay, so this is h of x. H of x is x plus 1 all cubed plus 8. And we know that h of x is equal to 0, which means that that has to equal 0. And so that means x plus 1 all cubed equals negative 8, which means that x plus 1 is the cube root of negative 8, which is negative 2. And so x is equal to negative 2 minus 1, which is negative 3. Okay. Another way we could write that same information is that h of negative 3 is equal to 0. When we make x negative 3, we get 0. Okay, so hopefully we're getting more familiar and more comfortable with that function notation. As I've said, it really is important going forward. Alright, so let's have a look at an example with some function notation. We've done questions like these a number of times before, but let's just refresh our memories again. So f of x is equal to 6 minus 3x, g of x is equal to x squared plus 4x minus 12. So f of x is a linear function, g of x is a quadratic function. We want to find these various things. So g of 0, which means we're going to apply the rule g. The rule g says you square your input, you add that together with 4 times the input, and then you subtract 12. So if the input is 0, we're going to square 0, we're going to add that together with 4 times 0, and then we're going to subtract 12. Okay, we're making the input 0, which means everywhere there's an x, it becomes 0. So in this case, that leaves us with negative 12. Part B, find x when g of x equals 0. Okay, so this is not making x 0, this is finding what x is when g of x, that is g of x, okay? If g of x is equal to that and g of x is also equal to 0, these two things are equal to each other. X squared plus 4x minus 12 is equal to 0, okay? So let's see if we can factorise that. 2 and 6, so x plus 6x minus 2 will factorise. And so therefore x is equal to negative 6 or x is equal to positive 2. So g of x is equal to 0 when x equals negative 6 or when x is equal to 2. So for that we could write that same information in a different way as g of negative 6 is equal to 0, g of 2 is also equal to 0. That's not what the question asks you to do. The question asks you to find x. Found x, make sure you answer the question. Okay. F of negative a quarter. So now we take our function f and we apply the function f, which is to subtract 3 times the input from 6, and we do that when the input is negative a quarter. So we're going to subtract 3 times the input from 6. Okay, all we're doing is substituting negative a quarter into the function. So that is 6 plus 3 quarters. 6 is 24 quarters plus 3 quarters, and so that is 27 quarters. Oops, quarters. And then part D, find x when g of x is equal to f of x. Okay, so this is g of x, this is f of x. Okay, so g of x is equal to that highlighted in yellow and f of x is equal to that highlighted in blue. And so therefore the equation we're trying to solve is when x squared plus 4x minus 12 is equal to 6 minus 3x. That is when f of x is equal to g of x. Okay, and we want to solve that for x. We've been asked to find x. Okay, so x squared, I'm going to add 3x to both sides, so it's plus 7x. I'm going to subtract 6, so that's minus 18. Okay, so this factorises again. Factors of negative 18 that add up to 7 are going to be positive 9. So it's x plus 9 and negative 2. And so we get x equals negative 9 or x equals 2. Again, answering the question says find x. We have found x. Okay, so the next idea we want to talk about is an idea of domain and range. So we can have domain and range of relations as well, but we really focus mostly on functions in the Maths Methods course. But domain and range isn't just unique to functions, it's anything you can draw on the Cartesian plane has domain and range. But essentially the domain of a function is the set of input values, so the x values, and the range of the function, a function is the set of output values, y values. Now, next year we'll talk in more formality about what it means to talk about a set of numbers and particular notation around that. So for now, this year we're going to be quite lax about how you go about describing the set of numbers and the notation you use, and we'll formalise that next year. We just want to get that sense of what do we mean when we're referring to the domain and what do we mean when we're referring to the range. So, for example, we can consider the domain and the range of the function y equals x squared by considering its graph. Okay, so as I said, the domain is the set of x values. Okay, so what x values does this graph exist for? Or the better question is, are there any x values where this graph doesn't exist? Now you can also think about this algebraically. Would there be any numbers that I could substitute into this that it wouldn't be possible to square them? And there isn't. Okay, so in this case, and the other way you can think about it with the graph is when you're looking at the domain is you're trying to identify the set of x values. So thinking about the x-axis, okay, so the set of numbers on the x-axis for which the graph exists. Okay, so one way you can do that, I've seen this explained before, is imagine like sort of having a strip of light above the x-axis, and the light's shining down on the function and the axis, sets of axes. And so the question is, the domain would be the set of the x values, the amount of the x-axis which is in shadow. Now in this case, I mean obviously we're only seeing part of the parabola. The parabola goes on, the parabola goes on and on forever. Okay, so obviously imagine that light source is up infinitely high above, the parabola that goes on for infinitely long, but thinking about how much of the axis would be in shadow. So if I imagine sort of zooming out this parabola, it would look something like that. The light's going to be blocked here and here and here, and so in fact what we would see is that the entire x-axis would be in shadow. So the domain is every possible x value. Now, one way we can write that is we can say that the domain is where x is between, oh no, not equal to, between negative infinity and positive infinity. That would be one way we could write that. Now, I was particular there, it's not correct to write bigger than or equal to negative infinity, and that's because you can't ever equal negative infinity. It's not a number, it's not a place you get to, it's the idea of something very, very big negative, okay? Similarly, we can't ever get to positive infinity, so x will have to be less than infinity. So we could write it in that way. As I said, next year we'll deal with some more formal notation, but another way we can write it, which is neater and easier, is to use the letter R, which means all real numbers. Okay. Now, when we draw an x-axis is a number line representing every single real number. Okay. Yes, there are non-real numbers. There are numbers called imaginary numbers, which if you study specialist maths, you'll meet imaginary numbers. But in math methods, everything we deal with is in the real number system. So when we say that the graph exists for all x values, we're suggesting it exists for all real numbers. Now, I think in your textbook, it doesn't use either notation. It just writes out a sentence, and it says that the domain is all real x values. So you could write out a sentence if you prefer to. But actually, all real x values can be much more easily represented by using the letter capital R. Okay, the range. Now, if we think about the range, it's thinking about the y values. For what y values does the graph exist? So again, we could imagine sort of having a light source, a vertical light source that's shining light horizontally towards the y-axis, okay? And what we want to think about here is how much of the y-axis would be in shadow. So again, our parabola goes on and on and on. So all of this is going to be blocked from the light source. All of this is going to be in shadow. So these y values will all be values where the parabola exists. So they would be part of the range. However, down here, the light can get through down here, okay? So these y values are not part of the range of this function, okay? It's not, there are no points on this graph which have a y coordinate that's down here, okay? And so these y values are not in the range of this function. So the range here, there is a y value of 0, that's the point 0, 0, so that's the smallest possible y value, but then every y value above that, there'll be a point on the graph that has a y coordinate with that value, okay? And so therefore the range is all of the y values that are bigger than or equal to 0, okay? All right, let's have a look at an example. So state the domain and the range of, state the domain and range, that should say of, the function f of x equals negative x minus 2 all squared plus 3. So we need to think about, this is clearly a quadratic function, hence its graph will be a parabola, okay? It's reflected in the x-axis, so it will be a sad parabola. It is translated to the right by 2 and up by 3, so the turning point will be at 2, 3. So we don't need a perfectly precise drawing here. I don't need to work out all the y-intercepts. The key idea is that it's a sad parabola with its turning point at 2, 3. Okay. So if we think about the domain of this function, let me just move that graph down a bit. If we think about the domain of this function, it's the x values where this graph exists. So again, imagining a light source above shining down. Are there any x values? Now, this is a bit problematic, so you might have to imagine the light source shining in both directions, so for anything below the x-axis. So for example, these bits down here, the light's going to be blocked from getting to the x-axis. These bits up here, the light's going to be blocked from getting to the x-axis here. It's possibly a slightly more confusing metaphor than helpful. If it doesn't help you, please ignore it. It's not how I would usually teach, but I heard it recently and I thought it was kind of a nice way to help some of you visualize what's happening. So it's essentially, though, are there any x values where this graph wouldn't exist? So algebraically, you're also thinking about, are there any numbers that I could substitute into that formula where I then wouldn't be able to calculate the value? And the answer to that is no, because it doesn't matter what x is, I can always subtract 2 from it. It doesn't matter what I'm squaring, I can square everything. There's no restrictions about squaring. Positive, negative, fraction, decimal, pi, you can write pi squared. Any number can be squared, so there's no restriction there. We can then multiply any number by -1, and we can then add 3 to anything. So there's no restrictions here. So the domain, the x values, there's nothing that wouldn't be possible to sub into here. And so then again, the domain is all real x values. Okay, and that is, we can write that as R. Now the range here is not going to be all real y values. This graph doesn't exist for all y values. There's a whole lot of y values up here where the graph doesn't exist at all. Okay, so again, you might, if you think about this sort of light source idea, shining light towards the graph, we would have the axis would be in shadow from here down because it'd be blocked by the function, but we're going to be able to get through up here. So that's not part of the range. So the range of this graph would be for all y values from 3 down. There would be a point somewhere on this parabola with, we could pick any y value from that's less than or equal to 3, and there would be at least one point on the graph with that y coordinate. And so the graph exists for those y values. So the range would be all the y values that are less than or equal to 3. Okay, so as I said, all functions we've looked at so far are polynomial functions: linear, quadratic, cubic, quartic, and they all have a domain of all real numbers. There's no restrictions. You can square, cube, raise to a power of 4, 5, 6, 7, any number. So there's no restriction at all in those. So let's have a look at a couple of examples of functions where we do start to get some restrictions. So that is that the graph doesn't exist for all of the x values. Okay, so let's think about the function y equals square root of x. So let's not think graphically because we haven't looked at this graph, but let's think algebraically. Are there any x values that we couldn't square root? And there are. We know that we can only square root numbers that are bigger than or equal to 0. Okay, so that tells us that whatever's underneath the square root here, it has to be bigger than or equal to 0 for that to exist. And so that's the domain. The domain of this graph and this function only exists if x is a number that is bigger than or equal to 0. As long as it's a positive number, you can calculate the square root of it, and therefore you can work out, and therefore this function exists for that x value. But if x was a negative value, we can't calculate the square root and the function doesn't exist. So the set of allowable x values, so we've seen this sort of thing when we've looked at application problems for suitable x values. Okay, so and in those situations we've been restricting the domain. We didn't call it the domain at the time, but we've been restricting the domain based on the context. So for example, can't have negative time and can't have negative height. So we're only interested in when t is bigger than or equal to 0. And sometimes even less than that, because we're also only interested in a graph that stops at this point. And so we would only be interested in t between 0 and whatever that point is. So we're looking at the set of x values for which the function exists here, and it's not around context. So we can't calculate square root of anything negative, and so therefore we can only calculate this function if x is bigger than or equal to 0, and that is the domain of this function, the x values for which the function exists. So if we use the same logic, we should be able to calculate the domain of some of the following functions. So again, the same logic applies. You can't square root something that is negative. So the only way this particular function would exist is if x plus 2 is bigger than or equal to 0. The thing under the square root is going to have to be bigger than or equal to 0 in order for that function to exist. And then we can solve this equation for x. So this means that x has to be bigger than or equal to -2. And so the domain here is that this function will exist as long as x is anything that is bigger than or equal to -2. If it equals -2, we'll be calculating the square root of 0, which is 0. If it equals -1, that'll be the square root of 1, that exists. -20, square root of 22, that exists. Okay. However, if x were to be -5, then we would be trying to calculate the square root of -3, and that doesn't exist. So that's why x can only be numbers that are bigger than or equal to -2. Same logic here. The thing under the square root, 1 minus 3x, has to be bigger than or equal to 0 so that we can take the square root of it. So 1 has to be bigger than or equal to 3x. I'm just solving for x now, dividing both sides by 3. And so what we're seeing here is that x has to be smaller than or equal to 1/3 in order for this function to exist. And so the domain is where x is less than or equal to 1/3. If you sub in any number that is bigger than 1/3, you'll be trying to square root a negative value and you'll have problems. All right, let's have a look at one more example. Consider the function y equals 1 over x and state the set of allowable values of x. So this is another situation when we have fractions where we get there are values of x for which this won't exist. So thinking about the fact that x is in the denominator of the fraction, and we know that we can't divide by 0. Okay, and so we know therefore that x cannot be equal to 0 or we would have a problem. Okay, so the domain is all real x values, so it can be anything just except for 0. Okay, and again, we'll look next year at notation we can use to describe that. We can use the same logic to state the domain of these two functions. Okay, so again, we can't divide by 0. It's not possible. And so any number that would make the denominator of the fraction equal 0 is going to be a problem. So we know that x minus 5 cannot be equal to 0, which means that x cannot be equal to 5. And so therefore, the domain of this function, and we'll be able to sketch these graphs in a couple of videos' time, the domain, and we'll see what's happening with this domain. So the domain is all real x values except for 5. Okay. And then this one, so again, we can't divide by 0. It doesn't matter that there's something up here. We can divide anything by anything that isn't 0. We can have 0 in the numerator. That wouldn't be an issue either. The issue is when we have a denominator of 0. So we know that 3x minus 2 cannot be, minus 2 cannot be equal to 0. And so 3x cannot be equal to 2. And so x cannot be equal to 2/3. I'm just solving that equation. So the domain here is all real x values except for 2/3. And as I said, in a couple of videos' time, we'll have a look at sketching these kind of graphs in example 4, and you'll see how that shows up on the graph, that we want to draw the graph for all x values except at one particular value. We'll have a look at what happens there. Okay, so the work today is some work from exercise 7H, looking at functions versus relations. How do you decide something is a function? So using your vertical line test, and then talking about domains and ranges of functions.